Hi everyone, this is lecture 4 of engineering mathematics from Notre Dame. So today we're going to review a few basic operations. Some of them we already have seen on matrix multiplication, inversion, and transpose. And also we're going to introduce concepts of elementary matrices such as permutation matrices and the like. I remind you that most of the material in the lecture today and in all of our linear algebra lectures follows very closely the textbook by Professor Strang that you need to go and read, both to get insights on whatever I'm talking on these lectures, plus many additional information on problems and even some implementation aspects of the things we're learning. Okay, so let me go back and review very rapidly the column and row views of AX equal to B. So in principle, we have seen this before, but I wanted to be sure that it comes across as clearly as possible. So let's go back to the row view of a linear system of equations. And as you can see here, my linear system is a trivial system of a 2x2 matrix A with a given vector B on the right-hand side. So what the row view is nothing else but interpreting basically this equation as two lines resulting by operating the first row 1 minus 2 on the vector xy and the second row 3, 2 on the vector xy to get 1 and 11. So the intersection of those two lines that you extract from the rows, they basically give you the solution to the linear systems of equations. And all of this is, of course, with the assumption that this linear system of equations exists. So that's the row view, and we can actually extend this to 3 dimensions. In 3 dimensions, of course, we're not going to be talking about lines, but intersecting planes. So if we have a system of equations of 3 by 3, you can easily look at the equations you extract from each row. Each of them defines a plane, and you can operate 2 planes at a time. So, you know, if you take the first 2 rows, they correspond to the planes that you see in the left plot. They intersect on a line L, and then you can take the third plane defined by 6 minus 3, 1, dotted with xyz equal to 2. That's the third plane, and the intersection of the third plane with the line defined by the intersection of the first 2 planes, of course, gives you the solution 0, 0, 2. And you can see actually that the solution is indeed 0, 0, 2. If you put x and y equal to 0, you multiply the third column by 2, you basically get 6, 4, and 2. All right, so that's the row view of the system of linear equations. And now we can go back and review once more the column view of linear systems of equations. So what I'm going to do is I'm going to start with the same trivial system of 2 by 2 equations, and I'm going to write it now as a combination of the 2 columns 1 and 3 and minus 2 and 2. The combination is defined by x and y. So you can see in the first equation is x minus 2y, and you can see I have x minus 2y equal to 1 and 3x plus 2y equal to 11. So I have a combination of 2 columns equal to b, and I'm asking, can you find x and y so that I can generate a vector 1 and 11? So if I can find that, then I have a solution to my linear system of equations. As the statement here indicates, of course, this idea can be generalized in matrices n by n. So if you have an n by n matrix with columns a1 to an, the product AX is basically a combination of the columns, and you're asking, can you find this combination that gives you B? So if B is in the column space of A, then there is a solution, and this is the column view of the system of linear equations. So my particular 2x2 example, if you want to visualize it geometrically, we have two vectors. Vector 1 is 1 and 3. Vector 2 is -2 and 2. And you can see 3 times vector 1 plus 1 time vector 2. It gives you the right-hand side, b equal 1 and 11. Of course, in these examples, we assume that a solution to the linear system of equations exists, and that's why we can get nice graphical representation. All right, let's do a 3-dimensional example. If we have a system of 3x3 of linear equations defined by a 3x3 matrix, this is the same system as before, so we know the solution is 0, 0, 2. So for this system of equations, the linear combination of the columns is basically 0 of column 1, 0 of column 2, and 2 of column 3 gives me the right-hand side, which is the vector b. And if you want a geometric interpretation, the 3 vectors are shown here, 1, 2, and 3. And basically, to get b, you only need 2 times vector 3 in this particular example. Okay, so this is the view of Ax equal b by paying emphasis to either the rows or the columns of the matrix A. All right, so let's next discuss a little bit about matrix multiplication and revisit some of the things we have seen to be sure that everybody gets the idea of the different ways of manipulating with rows and columns the multiplication of A times B. So the classical way that you look at the multiplication of A times B is by multiplying, for example, the I row of matrix A with the j column of the matrix B to get the element Cij. And this summation here is nothing else but the I row of A with the j row of B. If you take the inner product of those two, you get basically the element Cij. What I want to do is I want to use 2 different interpretations now of the multiplication, starting with a column view. So let's look at the product A times B that I call here C. I write B as the column B1, the column B2, and the column BP. P here, the matrix B that I'm using is n times P. The matrix A that I'm using is m times n, so the n and n match here. So the product comes to be a matrix m times P. So B has P columns, and I can write the product of A and B as AB1, AB2, ABP. So every column of the matrix AB has this form, and you can immediately see that each of these A times B is nothing else but a linear combination of the columns of A. Why is that? I remind you that when we multiply from the right a matrix, we get a linear combination of the columns. So if you take A times BI and you write A in terms of its columns times the components of the vector BI, what you do get is you get a linear combination of the columns of the matrix A. So effectively, the way that we look at multiplication here, every column of the product A times B is basically a linear combination of the columns of the matrix A. And again, A multiplies, comes from the left in the product. We can actually do almost the same idea here, but using rows to see if we can reproduce the product A, B in terms of rows, this time not of A, but of B. So let's see how this can possibly work out for us. So I can take again the product A times B, and I keep B as is, and I write A in terms of its row vectors. So each of these terms that you see here is one row of the matrix A. To make it, to remind you that it's a row vector, I use transpose, and to remind you that this vectors A1 So basically A1, curly A1 is the column that corresponds to row 1. Curly A2 is the column that corresponds to row 2. So they're not column vectors of matrix A, right? They are column vectors, but not of matrix A. They're column vectors that are used to define here the rows of A that I denote with these weird symbols that you see. So A times B would be A1 transpose. Oops, let me go back. A1 transpose B, A2 transpose B, AM transpose B. So basically, immediately you can see that every row of the product AB has this form of A transpose B. And we can see now with the second equation that each row of this product AB, it's nothing else but a linear combination of the rows of the matrix B. And you can see this by taking, let's say, a typical product AI transpose B and writing this row vector in terms of its components times the rows of B. And then immediately you can see the linear combination of the rows of B's gives you basically the product A times B. So effectively what we have done is we can look at the product AB as columns that they are combination of the columns of A, or we can see it as rows that they are combinations of the rows of B. Okay, of course, both of them lead to the same identical results. All right, let me be more elementary now by taking a 3x3 matrix that you see here. I don't use numbers just to make it more general. And so what I'm going to do is I'm going to multiply this matrix with 3 different row vectors to see what the effect is. And I'm going to remind you that when you multiply from the left with a row vector, what you get is you get a combination of the rows. So if I multiply the matrix A with the vector 1, 0, 0, the combination of the rows I get is only the row 1 because the row 2 and the row 3 are multiplied basically with zeros. Okay, so if you want to extract the row 1, effectively you can multiply on the left with a vector 1, 0, 0. If you want the second row, what you do is you multiply with a vector 0, 1, 0, and that's practically the same. If you want now to do a combination of rows, so let's say that you want to extract the third row, okay, minus 4 times the first row. So this is your combination that you are interested. So the vector on the left that you multiply is minus 4, 0, 1. So that will give you basically the third row minus 4 times the first row. Okay? So what I'm going to do now on the next slide, I'm going to take these 3 row vectors that you see on this slide, and I'm going to put them together as a matrix, okay, to see what is the effect of all of these 3 operations that you see on this slide simultaneously on my matrix A. So here is the matrix, how it looks like, okay. It's basically each of its rows is the rows that row vectors that I had before, and I multiply with my matrix A, and effectively the results are exactly what you expect. The first row doesn't change, the second row doesn't change, and the third row is substituted by the third row minus 4 times the row 1 of the matrix. Okay, this is exactly what I had before. So this matrix E1 that you see here, it's called an elementary matrix. It performs elementary row operations that we defined in lecture 3. And in our case, the operation that we performed was substituting effectively the third row with the third row minus 4 times the first row. Okay, that's the type of operation we did. All right, so we subtract 4 times row 1 from row 3. Somebody may want to ask you, how do I invert this process? What's the inverse of E1? So if I want to go back from this matrix back to my original matrix, what matrix do I need to multiply? What is the elementary matrix Obviously, the elementary matrix will be the inverse, but how will that inverse look like? And the answer is actually the inverse matrix will look almost identical to the original matrix E1, but instead of -4, I'm going to have 4 now. Why 4? Because now what I'm going to need to do to this matrix is I'm going to need to take the third row and add 4 times the first row so I can go back to my original third row. And you can actually verify that indeed when you multiply E1 inverse from the left with this matrix, you will actually get back your original matrix. Also, if you want, you can verify that this is indeed the inverse. So if you multiply this with E1, basically you will get the identity 3 by 3 matrix. All right. So let's do 2 more examples. Let's consider this matrix A2 that looks a little bit different. What's the effect of E2 on a matrix, the matrix A that we have? And again, you can think of each row multiplying A on the left, basically does linear combination of the rows of A. So if you look at the first row, what it will do is it will go and instead of in the first row, it will put a second row. And similarly, if you look on this, it will take on the second row of the new resulting matrix, it will put the first row of the original matrix, and it will not touch. It will not touch basically the third row. So the resulting matrix that you see here, what it does, it permutes the 2 rows. It exchanges the 2 rows. In row 1, it puts row 2, and in row 2, it puts row 1. This is what we call a permutation matrix, and it's very fundamental for the type of calculations we want to do in elimination processes that we will see on lecture 5 in the course. The third matrix, it's trivial. Basically, it does not affect row 1 or row 2, but it multiplies row 3 by 5. Okay, so let's go back to the permutation matrices, the exchanging rows 1 and 2 that you see here. I denote this with subscripts P1, 2 to emphasize that I'm exchanging rows 1 and 2. I'm going to give you a very fundamental property. If you ask, like before, what do I need? Let's say if I exchange rows 1 and 2, and now I want to take the resulting matrix and multiply from the left with another permutation matrix to go back to where I started. So if I want to multiply with the inverse, how will the inverse look like? Well, the inverse is actually equal to the transpose of the permutation matrix. This is an extremely important property for permutation matrices. Obviously, this equation indicates that the permutation matrix is not singular, and the inverse is equal to P transpose. What I want you to think is, I want you to think of the permutation matrix as a matrix that does actually exchanges of rows of the identity matrix. And I'm going to show you this in an example on the next slide for 3 by 3 matrices. So it does an exchanges of rows of the identity matrix. And if I have an identity matrix n by n, the number of exchanges of rows that I can do, including keeping the original identity matrix, is actually n factorial. N factorial, remember, is 1 times 2 times 3 times n. Okay, so if I have a 3 by 3 matrix, the number of permutations that you can get is 3 factorial, which is 6. And I'm going to show you this in the following slide. For those who are more interested in mathematics, I can say that this permutation matrices form what is called a multiplicative group. And so when you take courses on group theory, you will see this something to be covered in the very early lectures, and it's fundamental basically to lots of problems in physics, chemistry, and engineering. All right, so let's look at the permutation matrices, starting with the identity matrix in 3 by 3. So the idea here is very simple, right? if you look at the 3x3 identity matrix, you say which of the 3 rows of this identity matrix I can put in the first row of the new permutation that I will get. And the answer is you can put 3 different rows, right? You can put 1, 0, 0, 0, 1, 0, or 0, 0, 1. So 3 different rows can be on the first row. Once you select the first row, how many can you put on the second row? Well, you can put only 2. And once you select the second row, how many are left to put on the third row? Only 1. So for example, if you put the first row to be 1, 0, 0, 0, then the second row, you can put the 1 here, or you can put the 1 there, all right? Let me go back. We already have occupy 1, 0, 0, right? So the second row will be either 0, 1, 0, or 0, 0, 1. And then, of course, for each of these choices, the choice of the third row is only 1. So in the second matrix that you see here, the last choice would only be 0, 1, 0. So 6 permutation matrices for 3x3. Reminder, the inverse of the permutation matrix is P transpose. And even though we have not defined the determinant yet of these matrices, but you already know the concept from earlier courses, the determinant of a permutation matrix is plus 1 or minus 1. Okay, so it's a non-singular matrix with a determinant either plus 1 or minus 1. And we may later discuss when it is plus 1 or minus 1 as we use this in applications. All right, something more about permutations. If, let's say, out of curiosity, you say, how do I actually permute columns of matrices? Okay, rows, okay, we multiply with the permutation matrix on the left, but how do we do this with column matrices? Then the idea is you're going to have to multiply the matrix with the permutation matrix from the right. And I indicate this on this little 2x2 example at the bottom of the slide. So if you want to exchange columns 1 and 2, what you need to do is you multiply with this permutation matrix, and immediately you can see what the result is. So for example, when you multiply this matrix with the column vector 0, 1, if you remember, you take matrix times a column vector is combination of the columns of the original matrix. In this case, says take 0 of the first column and then 1 of the second column. So the first resulting column will be the second column of the original matrix, and the second resulting column will be the first column of the original matrix. So permutations from the right exchange columns, permutations from the left exchange rows. And of course, you can appreciate the fact that PA is not the same as AP, right? So remember, when you exchange the matrices multiplication, it's day and night. So don't expect P times A to be the same as A times P. Okay, let's look at something now a little bit more interesting. So what we're going to do is we're going to take a matrix A, M by N, and a matrix B, N by P. So in that sense, the product A, B is well defined. And we're going to take one column of A and one row of B. And when you multiply a column with a row vector, you actually get a matrix. You remember, X transpose Y gives you a scalar. That's our inner product. But a vector, a column vector times a row vector, gives you a matrix. And here is an example of a column vector, let's say from A, with a row vector from B. This gives you this interesting matrix, and I call it an interesting matrix because if you look at the columns, the second column is 6 times the first column of this matrix. Can you see that? This column here, 12, 18, and 24 is 6 times the first column, which means that the rank, that the dimensionality basically of the column space is 1. There is only one independent vector in the column space. Similarly, if you look at the rows, you will notice that all the rows of this product, they're basically multiples of the rows of the matrix B. all right, which in this case, the row of B that we use is 1 and 6. So this is 2 times 1 and 6. This is 3 times 1 and 6, and this is 4 times 1 and 6. So the column space involves multiples of the columns of A. The row space involves multiples of the row of B. So this matrix, the special matrix that we get by multiplying a column vector with a row vector, it's nothing else but a matrix that has rank 1. And you may say, why is all of this of interest? Well, look at this. How about if I take the product AB, okay, and I write A in terms of its columns, all right, this is what I have here. I write this in terms of its columns, and I write B in terms of its rows. Then the product AB is nothing else but the first column times the first row, the last column times the last row. And remember, each of these products is a matrix similar to what I had written on my earlier slide here. Okay, so effectively, what we have done is we have written the matrix AB as the sum of n matrices, each of them involving a column of A times a corresponding row of the matrix B. And each of these matrices basically has a rank 1. Effectively, both the row space and the column space of each of these matrices is just a line. Okay, so this representation, if you like, and generalizations of it will be very fundamental later on in the course in writing matrices in terms of rank 1 matrices. And we will do this not just for square matrices the way we have here, but for any sort of matrices using a similar idea. So this is a very nice representation of the product A times B. Okay, and I think I have a simple example of this. And if you take A and B to be these 2 by 2 matrices, you can write A and B as the first column of A times the first row of B, and the second column of A times the second row of B. And each of them is a matrix. And when you add them, hopefully with the correct algebra, you get the product A times B. Okay, so that is a nice way to look at the multiplication of A times B. Let me finish for now talking about multiplication and say that everything we discuss about the operations on taking products A times B, you can also apply it when A and B are partitioned in blocks. So in the case basically where what we call an element of A and an element of B, they are matrices themselves. So in this case, I have a matrix multiplication of A and B, but the elements of A11, A12, A21, etc., they're all matrices, obviously of dimensions between A and B that match together. So the partitions need to match. So in that case, if you want to write, let's say, the element C11 would be the first row of A, which is A11, A12, times the first column of B, which is B11 times B21. Okay, this is extremely important because lots of times we will be able to come up with nice ideas and algorithms using partitioning of matrices in matrices of smaller sizes. So remember what you learned about scalar elements, you can also apply it in the context of matrix partition. All right, so let me move to matrix inversion. So I'm assuming here that we're working with square matrices, an n by n matrix, and I assume that the inverse of this matrix exists, and I define it here. I call an inverse of a matrix A as a matrix I denote here as A minus 1, so that when I multiply A with A minus 1 from the left and from the right, I get the identity matrix. Okay? It's very important that in the definition to multiply both on the right and on the left with A minus 1. That's what we call an inverse of a matrix. So you can actually show that if the inverse of a matrix exists, actually this inverse is unique. And I give you a very simple derivation. If you have two inverses, B and C of a matrix A, so I'm going to use this multiplication from the right using B, so AB equal to I, and I'm going to use the multiplication on the left with the inverse C of A, CA equal to I, to show on the last equation that B and C have to be the same. So basically what I do is I say B is the same as the identity times B. The identity, I write it as C times A times B, and then I move the parentheses to AB, but AB is equal to I, so B equal to C. Okay? So if an inverse exists of a squared matrix, that inverse is unique. Now, the inverse comes with lots of nice properties that maybe you have used already in your classes. None of them is trivial, and all of them, they are sort of wonderful miracles of linear algebra. So let me just list all three of them. The inverse of the inverse is the same matrix A back. The inverse of the product is B minus 1, A minus 1. This is similar with the multiplication property of and transpose of the product AB. So the same thing for inverses. And here is a combination of the transpose property and the inverse. So the inverse of the transpose matrix, by a miracle, it is the transpose of the inverse matrix. You may say, yeah, I move the minus 1 inside, the transpose outside the parentheses. Well, yes, that works, but we will need to prove that indeed this is right, and it's not just magic. So let's prove some of this, and I think by the end of the lecture I will show you the second property as well for the inverse of the product. So, actually it's here. So if you have the inverse of the product, we said the result is B minus 1, A minus 1. You can prove actually that that's the right inverse. If you multiply from the right AB, you can see that by moving parentheses out, that B inverse will give you the identity matrix, and then A inverse will give you the identity, and you can do actually the same thing by multiplying from the left. You will also get the identity matrix. Okay, so here is a singular matrix, and you can immediately see that it's a singular matrix because you notice that the second column is 2 times the first row, so you only have one independent column here, and obviously also one independent row. So what I want to remind you is a good way to know when a matrix is singular. So in this case, we said the columns are dependent, the rows are dependent, but here is another way of looking at this. So I want you to concentrate on the solutions of the homogeneous equation, which is Ax equal to 0. Because the column 2 is 3 times the column 1, will you agree with me that the solution to Ax equals 0 is 3 minus 1, right? If you take 3 times column 1 minus column 2, you get 0. So effectively, this problem, Ax equals 0, has a non-zero solution. So when you have a non-zero solution to Ax equals 0, you can say with confidence that the matrix A is singular. Why is that? Imagine if it was not singular, then you can actually go, if A minus 1 existed, then by definition X would be A inverse times 0, right? A inverse times 0, and any matrix times 0 should give you 0. How can you get something that is non-zero? All right? So if you can identify a solution to Ax equals 0 that is not 0, you know that the matrix is singular. Okay, this is a very nice way to look at the invertibility of matrices. All right, so let's look at some final properties on the product. Reminder, we have seen this before, AB is not the same as BA. And if the product AB is 0, doesn't mean A is 0, doesn't mean B is 0. Here is another example. We have seen another example in an earlier lecture. If A is this and B is that, the product comes to be 0, but A is not 0, B is not 0, okay? And similarly, what that means that if somehow you have AC equal AD, don't go and cancel A out and say C equal to D. That may not be true in general, okay? So you may have a singular A that such that AC equal to AD, and that would not imply C equal to D. To imply C equal to D, A has to be invertible, this matrix have to be square, and then you can show that C equal to D. So actually the next theorem summarizes some of these properties. So if we have 3 square matrices n by n, we can show the following cancellation properties. If rank of A equal to n, that means if A is invertible and AB equal to AC, then think of multiplying this equation with A minus 1, then immediately you get B equal to C. Similarly, if A is invertible and AB equal to 0, multiply everything in AB equal to 0 by A inverse, and you get B equal to 0. And even more interestingly, if you have the product AB equal to 0, and A is not 0, and B is not 0, then based on this properties A and B, means that the matrices A and B have to be singular, okay? So if you have a product AB that is 0, and none of these matrices is 0, then you are dealing basically with singular matrices, so this is very, very useful. All right, and the last property is if A is singular, you can say that for the product BA and AB. BA and AB will also be singular. Now, just so we can finish with these properties, if there is an inverse matrix A, and you are looking for the solution to AX equal B, the solution obviously is X equal A inverse times B. Sounds trivial. Now, this solution not only is given by this nice formula, it's unique, okay? And this theorem, if you want to prove the uniqueness, you can concentrate on the last statement. If U is another solution, so that AU equal to B, you can show that U is actually the same as X equal to A minus 1 B. And the way to prove it is multiply AU equal to B with A inverse on both sides. A inverse and A give you identity. A minus 1 B is basically X, the unsolution we had before, and that way you can show that U equal to X. So the solution basically is unique for this linear system of equations, again assuming that A it's a square invertible matrix. Okay, so let me summarize with a few more things about matrix operations and transposes of matrices. So I remind you from an earlier lecture, once we defined the transpose, that gave us the opportunity to define the symmetric matrices, so the matrices that have A transpose equal to A, and also the skew symmetric matrices or anti-symmetric that have A equal to minus A transpose. And I think we have seen already plenty of times that the transpose of AB is B transpose A transpose. Okay, so let me, in the context since we are talking about the transpose, so let me summarize a few properties. If you have the product A times X, the transpose of that is X transpose A transpose. If you have a product of two matrices A, B, the transpose of that is B transpose A transpose. And if you have the inverse of a matrix, the transpose of the A inverse is basically the inverse of the transpose of A, okay? And the last property, just in case we did not prove it before, is given here. Very simple. if A minus 1 is the inverse of A, so A inverse equal to identity, take the transpose of that, still the identity. The transpose of the product is A inverse transpose times A transpose. So immediately, actually, from this equation, you can see, let me go back, you can see that this the transpose of A inverse is really the inverse of A transpose, because their product is equal to the identity, right? So we are done. We proved what we needed to prove. On statement 2 and statement 3, we see these concepts of inner and outer products. So remember, the inner product is, if we have two column vectors, the inner product is a scalar, okay? X transpose Y. We have seen this for vectors before. So the inner product of two vectors, one column, both column vectors, is X transpose Y. Now the outer product, that is written as without any dot in between, right? Without any dot in between, is X, Y transpose, where X and Y are column vectors. So if X is a vector n by 1, the if Y is also n by 1, Y transpose will be a vector 1 by n, and you notice the product becomes a matrix n by n, okay? So X, Y transpose, we call it the outer product of two column vectors, and it is a matrix of dimensions n by n. Finally, I wanted to show you something extremely fundamental to problems in all aspects of science, in engineering, in physics, in chemistry. You may wonder, from where did A transpose come? Why do we really care about the transpose of the matrix? So I want to show you an identity that is fundamental to physics, from where this A transpose comes, okay? So let's say that we need to compute the inner product of AX. So A is a matrix times X. So inner product with another column vector Y, okay? So by definition, this inner product is the transpose of AX times Y, right? That's how we define inner product. And if you take the transpose of AX, is X transpose A transpose Y, which is, you know what? Is the transpose, is the inner product of X with A transpose Y, by definition of the inner product. So actually, you can immediately see that AX dot Y is equal to X dot with A transpose Y. And I don't want to throw ideas from where is this coming in physics, but let me just say, practically every single problem that you will learn in applications in physics and engineering that involves inner product, and you can think inner product comes in calculating, for example, the energies, force, time, displacements, and things like that. Somehow, that's where the transpose of a matrix comes, and that matrix can represent things like the stiffness, and many other quantities depending on the type of application that you are looking. So A transpose, there is a need to play with it because physics requires the presence of A transpose in calculating this type of quantities that involve inner product of AX and Y. Okay, so we have defined the symmetric matrices as S transpose equal to S. These are very special matrices. We will spend lots of time in our course on this. If the matrices are symmetric, maths of the algebra will be simplified. So we love symmetric matrices, okay? And notice something interesting. If you have a matrix A, and it doesn't have to be square, it doesn't have to be symmetric matrix, A transpose A, it's always symmetric. A transpose A is always symmetric, right? If you take the transpose of A transpose A, you get the same matrix back. And we will see in this course that A transpose A comes very naturally in many different applications. Okay, so we will see this matrix A transpose A all the time. I am not going to say much about orthogonal matrices yet because we have not really talk about orthogonality, but some of you already may be familiar with the concept of what we have seen orthogonal vectors before. So let me just say, if you have a matrix Q that has columns that are vectors that are orthogonal to each other, then we call this matrix an orthogonal matrix. And this is also a very, very special matrix because the inverse of that orthogonal matrix is actually equal to Q transpose. Okay, so a matrix with orthogonal column vectors is called an orthogonal matrix, and it has a special inverse which is equal to Q transpose. Fantastic property, and so being able to actually work with orthogonal matrices, this is very fundamental to a lot of the linear algebra calculations. Okay, we talk about permutations, and we also talk for permutations. We actually have a very similar equation for the inverse of a permutation as we have for orthogonal matrices. So P inverse is P transpose, and we also gave some examples that for n by n matrices, we have a total of n factorial different type of permutations. So let me finish by proving actually the second identity, that the transpose of the matrix AB is actually B transpose A transpose. Okay, we use it, we took it for granted, but let's try actually to prove it. So I'm going to go directly to the statement here. A times B is I'm going to write B in terms of its columns. So remember that each column of the product AB, it's a combination of the columns of A. We have seen this before. So AB1 is the first column, AB2 is the second column. So when you take the transpose of AB, these columns are going to become now the rows of AB transpose, okay? So B1 transpose A transpose is the first row of the transpose of AB. B2 transpose A transpose is the second row of AB transpose. But you know what? This matrix here, the AB transpose, is literally B transpose A transpose, because B transpose I can write in terms of its rows times A transpose, and this is nothing else but what we have here. So AB transpose equal B transpose A transpose. Let me see, I think we are practically done, so let me just finish with this homogeneous system Ax equal to 0. And I remind you, a good way to check if the matrix A is singular or not, if you can find non-zero solutions to the homogeneous system, then you know that the matrix A is singular, or in other words, that its rank is less than n. And actually, if you want to relate things with concepts of determinants that you have seen in earlier courses in your linear algebra, you can affiliate this a singular matrix with singular rectangular matrix with a matrix that has zero determinant. We will come back to the concept of the determinant. We haven't really defined it yet. We didn't really need it as of now, but in case you're curious, a singular matrix, basically as we have defined it in terms of its rank and independent number of rows and columns, also that's the singularity is equivalent with the determinant of A being equal to 0. All right, so I'm going to finish here. It has been a long day, and we will come back on Wednesday to discuss the process of matrix elimination and how to represent, to do what is called the LU decomposition of a matrix A. So until then, enjoy the rest of the day, and I'll see you on Wednesday. Bye.